Join me in welcoming Jesse Johnson. So I'm going to talk about how this fairly abstract area of mathematics called hyperbolic geometry is related to a fairly concrete problem of data analysis, which is clustering. And I should maybe include a disclaimer that this is based on my work as a math professor, not so much on my current work at Google. But still will be interesting. So we should start just for a few minutes about what geometry has to do with data analysis. So, and I think this is probably fairly well known, just to make sure we're all on the same page. So, data analysis, data science is about taking, lists of numbers, data points, and kind of making predictions about new ones. And so you can think of those numbers as being coordinates of a point in some space. So, for example, two numbers for each data point, then you get two-dimensional coordinates in a plane, and then you can try to, and the idea, when you look at the left picture, you probably pick out some shapes, right? Our eyes, our brain is very good at shapes out of clouds of points, and so there should be some kind of underlying geometric shape, often called a probability distribution. So it's not, it's not necessarily something where it sort of has hard walls like we usually think of shapes, but it's still it can be kind of fuzzy. Different probabilities for different places. But anyways, that's the sort of shape that we're looking for. And so the idea, one way to approach data analysis is to think of this as the data points are random points sampled from some shape, and if we're given the data points, we want to infer what that underlying shape was, and then use our understanding of that shape to make predictions about new points or to do other types of analysis of that data. Okay, so this is very geometric, and so the kind of canonical example of this is classification, where you have two different types of points, the green and the blue, and the idea is to infer from that a shape, one shape for the green points and one shape for the blue points, and then if someone gives you a new point, well, you just look at which side that divide is on, it's in the green region or the blue region, and then that's the prediction that you make for which class the new point should fall into. So I'm going to talk about clustering, which goes kind of a step farther back. That is, given a collection of points and you don't know what the classes are, you don't know which ones are green and which ones are blue, you want to infer from that that there are 2 points, and you want to decide which of those points are green and blue based not on what other points are in those two classes, but based on just purely on the structure of the data of where all the points are. And so this is a little bit more tricky, and really, looked at from this perspective, requires a better understanding of the shape, a more subtle understanding of the shape. So, and then it's also a little tricky because so often you may not even be given how many different classes there are, right? So in this particular case, it's pretty easy to distinguish the blue from what was originally green, but you can see that the green and red, since we can see that they look like they might be two separate blobs that are just overlapping. So one question is, how do you pick out those more subtle distinctions? How do you decide if there are 2 blobs here or 3 blobs here? And how do you separate the kind of overlapping blobs? Blob is not a technical term, but okay. So so this requires a more subtle understanding of the geometry of that sort of underlying shape. Okay, so mathematicians. Oh yeah, and I should. Saying, right, I've been talking about two-dimensional data, but of course most data sets have lots and lots more numbers than 2 per data point, which means that we need to be thinking about higher dimensional geometry, which seems a little strange at first because there's only 3 dimensions, right? So how do you talk about 4 or 5 dimensional or higher dimensional data? Well, we can at least imagine that so 3-dimensional data, you can think about, you plot the 2-dimensional data in your desktop, and then you pull that up into the 3-dimensional space above the desk. So imagine that we're actually living, our 3-dimensional world is actually in the 3-dimensional desktop of a 4-dimensional being. So someone who lives in 4-dimensional space. So I like to call her Frida, 4-dimensional Frida. And so she sees our world in the surface of her desk, which is 3-dimensional, so she lives in 4 dimensions. And so after we plot the points in 3 dimensions above our desk, she can pull those out of her desk into the 4-dimensional space. And of course, Frida probably lives in the desktop of a 5-dimensional being, who can then pull those points in 5-dimensional space and so on. And so from a kind of, we can imagine that these higher dimensional data sets actually have some geometric meaning, even though we can't necessarily visualize it. And also, more importantly, it turns out that the mathematics that you use when you actually sit down to work out the technical details, it generalizes very well for these higher dimensions. And of course, there's this thing called recursive dimensionality, which is problematic, but as long as you take that into account, all of these techniques that work in low dimensions, you can at least determine what they would mean in higher dimensions, even if you have to watch out for the recursive dimensionality. Okay, so we can talk about pretty much any data set, even ones that don't have numbers. There are tricks for turning them into vectors, which you can think about as higher dimensional data points. So we can talk about the geometry of these data sets. Okay, but so mathematicians who have been studying higher dimensional geometry for a long time, so as far back as the mid-1800s, started to realize that you really want to distinguish between the geometry of a shape and what's called its topology. So the idea of topology is so with geometry, right? We think about rigid objects where you can move it around, you can translate it and rotate it, but it's sort of rigid. And any 2 points, the distance between them can't change. So the idea behind topology is you pretend that everything is made out of rubber, so you can actually change the distances between points. However, you can stretch things, but you can't rip them and you can't kind of smush things together. You can't glue things together. So the idea is, what can you do to a shape if you're allowed to bend and stretch it, but not to rip it? So from a geometric perspective, those top 2 shapes, the orange and the bagel, are they're basically geometrically they're very similar, right? Because they're both pretty round. Whereas the 2 shapes on the bottom, they're both more cylindrical, right? So geometrically, the rows are the similar objects. But topologically, from the perspective of topology, well, you can take that mug on the left, and you can kind of you either push the rim down, and you kind of pull the inside up, and then you can deform it into a ball, right? But if you were to try to do that with the mug on the right, well, you could certainly take the mug part of it and deform it into a ball, but you would still have this handle, right? You're not allowed to cut. You're not allowed to kind of squeeze that hole out. So no matter how hard you try, by just continuous step, so stretching and bending, you can only turn it into a bagel. So from the perspective of topology, the 2 columns are actually kind of the same, and the rows are different. Right. So somehow topology gives you almost a more qualitative understanding of what a shape is. It kind of picks out more fundamental structure than geometry. And so for clustering, right, what you want is somewhere in between geometry and topology, right? If we were to take these 2 sets and we were to sort of straighten out that curve based on the root points, or we were to take the red and the green and rotate them a little bit, the clustering structure would still be the same, right? We'd still pick out the same structures. Of course, for classification, we really want geometry, right? Because that would change the model that we used for classification. But for clustering, a little bit of bending and stretching actually shouldn't change the answer. And ideally, we would pick an algorithm where it didn't change the answer, since that's sort of somehow the structure that we want is it's not exactly topological, but it's closer to topological. Is that okay so far? All right. So let's see. Right. So the first step in kind of getting to a more topological understanding of a data set is, or one way to do this is what's called Similarity Graph. So this is a graph or a network, depending on which terminology you prefer. But basically, you look at your vector data, right, your points in space, and then you just connect them by an edge, or a link is the term in network theory. You draw a line between them if they're close enough to each other in some sense. And there are different ways of constructing these graphs. I won't go into too much detail about exactly that. You may even put a weight on the edge, where the closer the points are, the closer to 1. You have a number on there that sort of goes to 1 as the points get close together in the original space. It goes to 0 as they get farther apart. And so the idea of the graph is that, well, we no longer actually need the vector representation. We no longer need to think about them as points in space. This is telling us which points are close to each other. And somehow from a topological perspective, that's more important, right? Because when we bend and stretch, that just means we don't cut any of the edges. and then the other nice thing about a similarity graph, of course, is that you can use it for types of data that don't have a vector representation, such as, if you have a social network, then you can go straight to this graph and apply, any of the same techniques to it. Okay, so the similarity graph allows us, well, one thing it does is it allows us to start thinking more geometrically, that is, thinking more in terms of this underlying shape that we can't see but that we can infer. So for example, we can talk about the area of a partition, right? So here I've separated off the red points, and you can imagine if these were points in some, sampled from some three-dimensional object, and we were to cut the object in such a way that those points were on one side of the cut and the black points were on the other, then we'd have this two-dimensional surface separating them, and we might want to know what that area is. And the idea is that if we count up the edges that go from the red to the black, or if we add up the weights, if we're doing a weighted graph, that somehow we can think of that as an approximation of what the area of this partition would be. So this gives us a way of not measuring per se, but approximately measuring the geometric properties of what this underlying shape would be. And we can also talk about the volume of a subset of this graph, and so the obvious way to do this. So again, the idea is if these were sampled from some three-dimensional object, we'd want to know what's the three-dimensional volume of sort of the plate, the part of the object that they were taken from. And so the obvious way to do this would be to add up just the number of vertices. For various reasons, it's more common to add up the number of edges. So you add up the weights, or you just count the number of edges that go from red points to red points, and we call that volume. Okay, so now we have this notion of the area of a partition of a graph, and we have this notion of the volume of a subset of the graph. And so now we can start talking about geometry. So we haven't gotten to topology yet, but we will. So for example, we can you calculate what's called the Cheeger constant. So that's the mathematical term for it. There's a few different. So I think in computer science, normalized mean cut is more common. It's also supposedly related to the max flow mean cut. But anyway, so the idea is for any partition, so any way of separating the graph into red and blue, you calculate the area, so that is you count the number of purple edges between them, and then you take the volume of either side, and you divide the area by the smaller of the two volumes. And you want this to be as small as possible. So the idea of the Cheeger constant is to find the partition that minimizes this value. That's what the end is. Sorry, I think I first made the slide for applications, so I don't know if you guys all know. So you can write min instead of in, or you can think of that as an instant there in being on this doesn't matter. Okay, so the idea here, right, if we want to make this as small as possible, so we want to have as few purple edges as possible and make sure that both the red edges and the blue, both of them are as large as possible, right? Because that was the denominator what we did. So in other words, we want something that divides the graph as evenly as possible while cutting as few edges. So that would be something like this one here, right? And so the idea is, right, again, we want the cut to be as small as possible while still having a pretty even partition between the two sides, and so that's exactly the bottleneck. And of course, if we're clustering, right, if we wanted to cut this graph into two clusters, the bottleneck is exactly what we would be looking for as where we want to cut it. So this now gives us so now we're talking about geometry in a very real sense, and we're using it to say something about data sets. So the way that this is normally used in data analysis, so one way I should say that this is often used or is often calculated. Right? So the problem, maybe let's go back to this for a second. So the obvious solution would just be to look at all possible partitions of the graph and just calculate, that ratio for each one and just take the smallest, right? But obviously that's not going to work well because, there's 2 to the n different ways of partitioning this graph, and so that's going to take a while. That's not really feasible, especially for, probably for anything more than a few hundred. Anyways, that's not really feasible, so just given how big, how many partitions there are. So a common way to approximate the Cheeger constant uses physics. So the idea is if you were to take a drum that was lima beam shaped, this is sort of a mutated bongo drum. So it has an obvious bottleneck, right? And it turns out that if you were to hit this from and watch the vibrations. So the vibrations are very complex, but they're made up of these simpler waves, and the lowest frequency of these waves would have the property that whenever the left side is going down, the right side is coming up, and vice versa. It kind of goes back and forth. And the set of points where it's not moving at all, the set where you divide the down moving points from the up moving points, is exactly, or at least very close to the bottleneck. And that the close to is important. This gives you a good approximation of the cheaper class. It's not an exact solution, but there's sort of fundamental physics that tells you that finding these vibrations, which you do by calculating a partial differential equation called the Laplacian, that will give you a good approximation of the Cheeger constant. Turns out you can do the same thing with a graph. That is, you can take your graph and you can hit it with a mallet and watch how it vibrates. So you obviously don't do this literally, but you can calculate. There's a matrix called the Laplacian, and you can calculate its eigenvectors, and the lowest eigenvector will do the same thing as what happened when we hit the drum head, in that it'll tell you'll have some points that are sort of moving up, some that are moving down, and the points in the middle, the edges that sort of separate these two, will give us a very good approximation for the Cheeger constant. So this is sort of more on the physics side now, but still, so this is a good. And then of course calculating eigenvectors, it's not fast compared to some other methods, but it's a lot faster than looking at all possible partitions, polynomial instead of exponential. Okay, so here are some problems with this, and of course I'm going to tell you about my algorithms. So I have to first tell you about the problems with the old algorithms. So if you have unbalanced clusters, that is, you have a graph where one of the sides of the bottleneck is much smaller than the other, the Cheeger constant is still going to try and even out, right? It's going to try and give you balanced clusters, and so it won't always handle this situation well. It'll try to kind of it may put the balanced part before the finding the narrowest bottleneck. Another issue is that it will often tell, so this will tell you a way to partition your graph that minimizes the Cheeger constant, whether or not there's actually a bottleneck there. So if you have a graph like this, it will tell you how to separate it into two, even though that's not necessarily the way you do. Okay, so that's again, that's my that's the motivation for kind of continuing on other ways of approaching this problem. Okay, so now let's get into the hyperbolic geometry. So I put hyperbolic geometry in the title because I thought it would increase the audience size, get people excited, and then shortly afterwards I realized I would have to actually explain what hyperbolic geometry is in the 5 minutes or 2 minutes, something like that. So I'm going to do my best. So the idea is surface, right? It's a two-hole donut. The genus two surface is the technical term, right? So the idea is we're used to surfaces, but this is just a two-dimensional part of it. So this is not filled in. It's just a two-dimensional object that you see right in front of you. And if you look at this surface here, you can see that. So this is a topological object in the sense that we could stretch it. You could stretch it and bend it, and those two holes would still be there. So initially we're just thinking about this topologically. But of course this also happens to have a certain geometric representation right in front of us, and you can see that there are some places, so like on the inside of the, I guess I can use my mouse cursor. So at this point right here, right, it actually looks like a saddle, right? It looks like that saddle on the right. There's two places where it's coming up and two places where it's going down. In other places, particularly at the ends over here, it does not look like a saddle. It looks like a local maximum or a minimum. It's kind of bowl-shaped. It goes down in all directions. But it turns out that if you were to take the surface up into a higher dimension, you could actually lay it out, that is, find a geometric representation of it in which every single point looked like a saddle. So it looked like this saddle on the right. And so of course, you have to wonder, what does that mean in higher dimensions? Well, you can talk about this saddle shape in terms of just the surface itself and not its embedding. And then there's various ways to do this. One way is to think about how quickly the circumference of circles increases as their radius increases, right? In a flat plane, the circumference of a circle is equal to 2 pi times its radius. Whereas in the saddle, as the radius gets bigger, what happens is the circle kind of gets stretched down and up, and so its circumference actually gets a lot bigger. So if you were to, so for any radius, the circumference of the circle, all the points that are that distance from the center, would actually be quite a bit bigger than 2 pi r. And the bigger the radius gets, the more that difference, the bigger the ratio gets. So this is one way to define hyperbolic, to define the saddle, which actually makes sense in these higher dimensions. So the key to hyperbolic geometry or hyperbolic surfaces is that if you allow this sort of embedding in higher dimensions, or there's also ways to deal with it without ignoring the embedding, anyways, you can sort of deal with these geometrically in a way that every single point looks like a saddle, and moreover, every single point looks like exactly the same saddle. So if you lived on this surface, if you were walking around, you wouldn't be able to tell the difference between 2 points because they would all have the same exact saddle shape. So this is a homogeneous hyperbolic surface. And then the other neat thing about this is that you can actually, it turns out there are also lots of ways to do this. This is true for any surface that has at least 2 holes. So you can have a 3-hole surface and do the same thing and so on. The other thing about these hyperbolic surfaces is they're very flexible in the sense that if you told me how big you wanted each hole to be, I could, at least in some theoretical sense, find you an embedding where the holes were that size and it was still hyperbolic, where every point was this sort of saddle shape. So that's hyperbolic geometry. It's 2-dimensional hyperbolic geometry, but of course, in mathematics, it's never good enough just to do 2 dimensions. So we're going to do the same thing as we did with the data sets. We're going to think about what would this mean in higher dimensions. So not putting the surface in higher dimensions, but replacing the 2-dimensional surface with a 3-dimensional quote-unquote surface, what we call it a manifold. So in other words, so we're going back to 4-dimensional Frida, right? When she eats her breakfast in the morning, she has a bagel, right? What does that bagel look like? Well, it doesn't look like a 2-dimensional surface. It's going to be 3-dimensional. So it's going to be some kind of 3-dimensional object, right? So instead of talking about whether or not the points on that bagel are saddles, they're going to be some kind of 3-dimensional equivalent of a saddle, right? So we live in one of these shapes, right? The universe that we live in, or at least that we perceive around us, is 3-dimensional, right? And so it's Euclidean in the sense that the sphere of radius, what r is 3/4 pi r squared. I forget it's linear, or it's a quadratic. It has a certain. You can calculate its surface area from its radius. But when Frida eats her bagel in the morning, there's going to be some points that are saddle-shaped where the circumference of a sphere actually increases much faster than in our universe. And of course, it's very hard for us to calculate the surface of spheres that are larger than, maybe a few miles. So it's possible if we had, a 3 light-year sphere that we can calculate the area of, maybe it would be bigger. Maybe we actually do live in a hyperbolic universe. Okay, so sorry, I realize I'm getting into kind of very, very abstract mathematics here. I'm going to circle back to data, I promise, so just bear with me for a little bit longer. Remember, you came to this talk despite the fact that it's hyperbolic geometry in the title. Okay, so another way to think about this is imagine you're Magellan, right? So the surface here, right? If we lived on a 2-hole torus, right? Magellan, sailed around the Earth, right? He starts sailing, and maybe he just goes around one of these holes, right? He comes back. Well, how would he know the difference, right? If all he had seen was that little loop there. Well, similarly, imagine getting into a spaceship and flying off for thousands of light years, maybe longer. So you'd have to live a long time. But in theory, you could actually end up back where you started in Earth, right? By going around a kind of circle, just like Magellan did. And so in theory, we could live in one of these spaces. Okay, so that's 3-dimensional hyperbolic geometry. Okay, we're almost ready to start circling back. So 3-dimensional hyperbolic geometry, right knots. So what is a knot? A knot is what you get by taking a piece of string and gluing the ends together. Here's a good one. So this is a figure 8 knot. It's the same. It should be the same one that's up on the screen. I don't know if you guys can see that, either on the screen or me holding it up. So the idea is, what we want to do is we want to look at the space around the knot. So in other words, imagine that we were to take the universe that we think we live in, and then we were to cut a knot like that out of it, right? And the problem is, if you're flying a spaceship, you can't run into the knot, right? You can't actually hit the end of the universe. So the way we remove the knot is we make it infinitely far from everything. We kind of pull it, so that's the picture on the right, that's what we kind of pull it out infinitely far from everything. And this, of course, forces the rest of the universe to get all tangled up. And then it turns out if you do this, for this particular knot and many other knots, then the sort of tangled guts that remains of the universe, you can actually put a hyperbolic metric on them. It actually becomes a hyperbolic, quote-unquote surface, a manifold. Okay? So that's kind of cool, even though it's sort of hard to picture. But the other neat thing about this, so remember the surfaces, they were very flexible, right? There were lots of different ways to put a hyperbolic metric on it. The key here is something called Moscow rigidity, which says that if you have a three-dimensional or a higher dimensional equivalent of a surface with a hyperbolic metric, there's exactly one way to put that metric on there. Okay, so there's exactly one geometric structure for that, for this knot. So in other words, once you understand the topology of the knot, you completely, in some sense at least, understand its geometry. At least you've fixed its geometry. Which means that topological properties of this knot correspond to geometric properties of this hyperbolic space that we can't really imagine that's sitting to the right of it. Okay, so that's the key. Topology of knots is equivalent to geometry, and the same is true for other types of three-dimensional manifolds. Okay, so so let's talk about knots. Okay, so now we're starting to circle back. So one thing that mathematicians who study knots are interested in is, what do you do when a knot is made up of smaller knots? So so for example here, this picture here, you can see this knot on the left is made up of two knots called the trefoil knots, which is not like the cookies. It's spelled the same as the cookies, but it's different. It's a knot particular, it's not a cookie. Anyway, so we're basically taking these two knots and sort of pinching them together, and we get this one here. And so the question is, if someone gave you this knot, how could you tell that it came from the two smaller ones? Okay, so does that sound familiar at all? Right, so with our data sets, when we were doing clustering, we were interested in the problem of, if someone gives you a bunch of data points that actually came from two different classes, how do you tell that those two different classes make up this data set? So here we're doing the same thing, but with knots, which is topological, but again, topology for knots is really geometry. So somehow this is really telling us something about the geometry of the space around it. So what Dave Gabay figured out was that if you do what's called, so the idea is you kind of scan across the knot, you look at how many intersections you have at each point, and you try to make it so that it's as thin as possible. So that as these horizontal lines intersect the knot in as few points as possible as you scan across. And so obviously it's going to be fewer on the left than on the right. And you've got to keep track of, you do what's called lexicographic ordering, where 2 4s is less than 1 6. And what you get when you do that, so you make the thick parts as small as possible, and then it turns out that the thin parts are actually, well, you can see here, right? The thin part, the thinnest line on the left is the bottleneck, right? That's where we want to cut our knot into 2 knots. And there are some very precise ways in which you can state that and prove that I won't go into. So the key is that we have this way of looking for bottlenecks in knots. We know from hyperbolic geometry that this has something to do with bottlenecks in these hyperbolic spaces, right? These big geometric spaces, from Moscow rigidity. And we also know that we want to find bottlenecks, right? Low Cheeger constants in order to solve the clustering problem. So the question is, can we now do that directly? And it turns out we can. We even have time for it too. So let's just quickly go over exactly what we're doing here, right? So we're scanning across the knot, right? So we're moving this blue line from one side of the knot to the other. And as we do that, right, there's 2 different ways. We can go up and up and up and then down and up again. Or we can go all the way up to the top and then all the way down. So I'm probably not going to leave this slide long enough for you to really see that, unfortunately. But anyway, so there's different ways of scanning across this knob. And if we do the one that's finished, where we go down and then back up again, then there's an intermediate state that picks out the bottleneck. Okay, so here's a practical application of this. Right, so let's find a bottleneck on a Coke bottle. Okay, so we start off with a rubber band, and we want to stretch the rubber band over the Coke bottle in a way that stretches the rubber band as little as possible. Right, this is the sort of spinning thing. So right, the bad way to do it would be to stretch it over the top of the bottle and then back on the other side. Right, it would make more sense to start at the top and sort of go from the top to the bottom. Right. So now what we want to do is keep track of the tension on the rubber band. How far is it stretched? Well, it's going to be stretched the most at the very top when we go over the lip, and then the middle, and then at the bottom. And in between, there's going to be two places where it's stretched a little bit less than right before and right after. And one of those is, of course, literally the bottleneck. And the other one is at the bottom where Coke, the Coke bottles have this funny little indentation. Okay, so great. So we can find the bottleneck in a bottle of Coke, which isn't very useful. But imagine if this was a 100-dimensional Coke bottle or a 1,000-dimensional Coke bottle. So in other words, you couldn't actually see the bottle, but there was someone else, living in this higher dimensional world who could tell you. First of all, they could promise that they were doing this in the most careful way possible, that is, in the most efficient way, and they were telling you at every given time how much tension was on the rubber band. Well, if that was happening, right, you would find the bottlenecks just from knowing the tension on the rubber band, right? Because whenever it gets a little bit smaller and then gets bigger again, that's a bottleneck. Okay? Right, that's almost, I think that's a reasonable, you can take that as a definition of a bottleneck. Right? So that's exactly what was happening in this picture here, right? Where the number of intersections goes down and goes back up. I guess it's not exactly, but somehow it's geometrically, if you follow the analogy through this, what's happening. Okay, so we can find bottlenecks in bottles, which is not a particularly difficult task. But can we do this for graphs? Can we do this for the similarity similarity graph defined by data set? So here's how we do it. So the answer is yes. And here's how we do it. So we start off, we just put the vertices of the graph in some order. So we're going to do this for a very simple graph, right? 6 vertices. You can see there's sort of 2 clusters of 3. It might be a reasonable way to cut up this graph. So we just randomly choose an order on these vertices, and then what we do is we spread them along the line, and we look at how many edges go from the first, k vertices to the remaining vertices, right? So it's a little bit tricky to see, but the graph on the bottom is actually the same graph on the top, just with the vertices kind of pulled around to sit along this green line. And then we can count the number of edges, and what you see is that it goes 2, 3, 4, 3, 2, right? So there's a maximum at 4. So this picture is kind of like this one. This is basically the knot on the right, where the number of crossings goes up and up and up, and then down and down and down. Okay, so this gives us our initial ordering, and we get some numbers on there, that's sort of the tension on the rubber band. And then it turns out that there's a way to look for ways of reducing the number of edges crossed. And so this equation on the bottom, I won't tell you what S and A are, but the point is, you can calculate it. It's a quadratic time algorithm to calculate what these values are, and then you scan over the different possibilities, and you pick out the one where this difference is as high as possible, and then that tells you how to slide one vertex across and place it down between 2 other ones to reorder them in a way that reduces the number of crossings. And it doesn't reduce the number of crossings at the bottlenecks, it reduces the number of crossings at the thickest places, just like thin positions did. And so in this case, what this equation tells you is, so again, this one on the right is the same as it's the same graph as the one on the left. It's just that I slided one of the vertices over, and the other two can kind of fill in the gap. And so what we see is that after we do this move, right now instead of going 2, 3, 4, 3, 2, it goes 2, 3, 2, 3, 2. So that 2 there is where the number of edges goes down and then back up again. And so that looks like the bottleneck. Okay, so if we did this for a more complex graph, right, maybe one that we can't even draw on screen, right, what we would get, and this is probably exaggerated compared to a real-life example, but we get some graph that looks like this, where we see the width going up and down. And in fact, we see right here in the middle is what looks like a bottleneck, right? That's where the width goes down a lot and then goes back up a lot. And so if we're looking at this graph, or maybe, I mean, you could probably you can automate this as well. But anyways, we can pick out where what appears to be a bottleneck is. And you can actually prove that if you do this, that if you minimize the graph as much as possible and you pick out the local minimum, then the partition that you get is no longer, it's not going to minimize the Cheeger constant, but again, that's not necessarily what we want anyway. What it's going to do is give you what I call a pinch cluster, which has the property that if you were to slide any vertex across the partition, the number of edges crossing the partition would increase, right? So this is in some very real sense a bottleneck. And even though, you know, it's certainly true for the ordering that we have, it turns out it's sort of even stronger, you know, than just sort of that there's a dip with respect to the ordering. And the cool thing about this, at least what I really like about this, is that the proof is perfectly analogous with the proof that, you know, there's sort of an analogous proof for the knots, and then you can basically almost, you know, word for word translate that proof into, well, maybe not word for word, but certainly concept for concept, you can translate it into the fact that you get these pinch clusters. This is sort of, there's a small y here. Pinch cluster is actually more complex than that, because you could have situations where you can move vertices back and forth without increasing the width number of edges. But what you can show that what you do have is that in order to kind of move all the vertices from one side of the partition to the other, the number of edges that you cross has to go up before it goes down. So if you sort of generalize what you mean by a cluster, or sorry, by a bottleneck, then the still is a sort of good. This thing picks out bottlenecks. This algorithm picks out bottlenecks. Okay, so what you get is a way of taking a graph and turning it in. So taking a network graph and turning it into a plot. I guess this is also a graph, right? Anyways, you get something like this, where you can sort of pick out from this the maximum and the minimum width, and you can use this to decide which clusters are best in a way that you don't get with something like spectral clustering. So, for example, the minimum, this little minimum way over here on the right, is actually lower than the one in the middle, but you can see that it's probably not a good place to pick a cluster because, you know, the width for the right of it is very high, whereas this one in the middle looks like it kind of does a better job of partitioning the graph. Okay, so right, so we're in work with Doug Easterkamp, who's also in the state in the computer science department. We implemented this. It did some experiments, and it turns out that sure there are, at least on some data sets, obviously not all data sets, but there are a number of data sets on which this does better than many existing algorithms. So there is some real potential here. Now, I'm not claiming that this is, you know, so that there's still issues with scale, permutation, complexity, things like that. But I think what this shows is that there is kind of real potential to take these more abstract ideas from geometry, even hyperbolic geometry, and apply those to data science problems. So I think it still requires some work, but this kind of points out a good direction that this sort of approach can take. So having said that, I think I'll stop.